Sayo, I forgot to mention, SoME will be split up into 3 segments for each month. The first month here is the geometry section, then we go to calculus, and after that, complex analysis.
I understand. So, what's today's question?
Sounds simple enough, we just have to prove the Pythagorean theorem.
A squared plus b squared equals c squared, right? That's easy. I'll get back to you after the intro.
Yeah, I'll also be working on this. Wait, why are you looking at me like that?
You said this. Didn't we agree not to say that word last episode?
Yeah, I guess you're right.
So, my proof is rather simple. You take a bulk with side lengths a plus b and put 4 copies of the triangle in each corner. You get a square with side length c. Rearranging the triangles, you then get 2 squares, a squared plus b squared. Since the area of the empty space doesn't change, that shows that a squared plus b squared equals c squared.
That's nice. But my proof is different. See this? In this diagram, if you extend the top lines of the leg squares, it meets at a point such that this length equals c. If you shift these squares up to that line, you get 2 parallelograms. And if you shift the parallelograms down, they fit in the hypotenuse box.
There we go. Simple as that. Wait, why is there a timer? What? We have to prove this 32 more times? And in under 5 minutes? With the time we have left, that's like 8 seconds per proof.
Don't worry, Sayo. I think we can do it. Just trust me on this. First, let's take your proof and rearrange the triangles. The square now has a side length of c, so its area is c squared, but the area is also a small square, side length b minus a plus the forward triangle. Simplifying, we get c squared equals b squared minus a squared. Next, this one is half your proof. You can solve the area of the parallelogram in 2 different ways, and they both cancel out in the Pythagorean Theorem. This was made famous by a certain US president.
James A. Garfield, right?
Yeah, that one.
I think another proof goes like this. Scale the triangle up by b as an attached to the triangle scaled up by a, and you should get the triangle scaled up by c. Comparing the lengths, it becomes obvious.
Hey, remember this diagram from the first episode? Yeah, that's our next proof.
We also get a proof by turning the squares into the same triangle. You can solve the area by completing the rectangles and triangles highlighted, and also the other way.
Yeah, saying this without the word this is pretty hard. Anyways, here's another visual proof.
Next, draw a circle with the radius c. By the intersecting chords theorem, a times a equals c plus b times c minus b, and then we can apply the differences of squares.
In the diagram shown, there are several similar triangles. Using the ratio between them, we get the following formula.
Then, take a square with side length b and cut it this way. You can see you can rearrange the pieces into a square with side length c with a whole of side length a. Therefore, b squared equals c squared minus a squared.
Tony's theorem says for a cyclical quadrilateral, the sums of the product of the pairs of opposite sides equal the product of the diagonals. For the case of a rectangle, we get the Pythagorean theorem again.
Here's a diagram from the first proof, and here's a way to cut up the pieces of the square of side length c and rearrange them into the squares of side lengths a and b.
Triangles ABC and DEF are both the triangles in question. We can calculate the area of the full triangle thingy with 2 different ways. Substituting their values and you get the same.
Here's another diagram. Rearranging 4 copies of the diagram, you get whatever this is. And the area of this thing is 2r times a plus b plus c, but it's also 2ab. Since c is a plus b minus 2r, you can calculate it and add up with c squared equals a squared plus b squared.
Here's another visual proof, and here's a proof based on the tessellation. You can see that the 2 hexagons easily have the same area. Here's another proof taking 3 scale copies of the triangle and rearranging them into a rectangle.
That's just the previous proof stated differently.
Well, we're running low on time, don't judge.
Whatever. This proof uses the intersecting chords theorem, which I've shown on the screen here. And here's another proof based on calculating an area in 2 different ways, this time triangle ABD.
Did someone say proof without words? I think someone said proof without words. In 1896, 2 guys used the diagram shown to generate 4,864 proofs. Here's one of them.
Remember the intersecting chords theorem from a few proofs back? This is another proof using it.
Unfortunately, it doesn't work for isosceles right triangles, so here's one that does.
The parallelogram law states that for any 2 vectors, the square of the lengths of the difference but the square of the lengths of the sum equals twice the... Wait, we only have 1 minute left?
We need to hurry up.
Well, okay. You know what? The formula's on screen. Just read it. When U and V are normal, these two are the same.
Here's another visual proof. Heron's formula is a formula for an area of a triangle. S here stands for the perimeter divided by 2. Substituting that in and manipulating it, we get a squared plus b squared minus c squared equals 0. You can see for yourself that the highlighted areas are the same. This is the area for the isosceles triangle and this is the area for the other thing. A rare trigonometry base.
Wait, why are trigonometry truths rare?
It's rare because the most useful identity in trigonometry is literally just the Pythagorean Theorem.
Hey, wait a minute. The cos addition formula we derived last episode doesn't depend on it. Substituting alpha for zeta and beta for minus zeta, the left-hand side becomes cos squared alpha plus sine squared alpha, and the right-hand side just becomes 1.
Extend the triangle so that h is the midpoint of AB prime and apply the intersecting chord theorem. Use that to calculate the side of the hypotenuse.
4 seconds
Here are
left!
3 more visual proofs and one last proof based on the geometric series.
Finally, we are done!
If you want more information about these proofs, and even more proofs, check out the link in the description. Anyways, see you in SoME4. SoME4 episode 4, I mean. I'd probably be making the Teapot 18 YTP, but whatever, I'll see if I can get it out that time. Maybe, when for the most part you're just showing diagrams, the word this ain't too bad.
Isn't.